All right, let's do number 2 off of the antiderivative word problems, FRQ. All right, so number 2 says traffic flow is defined as the rate at which cars pass through an intersection. Okay, measured in cars per minute, so that's an important unit to keep in mind there. This is traffic flow is a rate. So traffic flow at a particular intersection is modeled by the function f. F of t is 82 plus 4 sine of t over 2 for t between 0 and 30. So between 0 and 30 minutes. So part A, to the nearest whole number, how many cars pass through the intersection? So we're given something that is that is a function that's defined as cars per minute. We're trying to move up. We're trying to move up our units to be the number of cars. So if I want to get from a rate to the value, I have to take the antiderivative. Okay, so the integral of my rate, cars per minute, over the course of the 30-minute period, I'm going to be able to accumulate those rate and arrive at the total number of cars. Okay, so we're going to accumulate this rate, f of t, over the course of the 30-minute period. So essentially, we're just multiplying that rate by 30. Okay, entering our calculator. I'm going to call that function there, so math 9 from 0 to 30. Okay, so we're going to round it to the nearest whole number, so 2474. So we started with cars per minute, and then now we're able to accumulate that rate up to the number of cars. Okay, part B, is the traffic flow increasing or decreasing at t equals 7? So traffic flow is cars per minute. We want to know the rate of change of the traffic flow, which means that we have to involve the derivative of f of t. Okay. So we want to find the rate of change of traffic flow so it's got to be f prime of t. We got to involve f prime of t. All right, and we want to find f prime of 7. So I have my f of t spelled out under y1. So I'm going to do math 8. D over dx. I'm going to call the function the traffic flow function. Vars, y vars, function y1. I want to evaluate the rate of change at 7. So we get a negative value, so we know that this is in units, this is going to be cars per minute per minute. So we can therefore say that traffic flow is decreasing at t equals 7. All right, part C. What is the average value of the traffic flow? So average value of the traffic flow, that's average value theorem for part C. Okay, so average value theorem is just 1 over b minus a. Integral from a to b of, in this case, f of t. We want to find the average value between 10 and 15. So we treat 10 as our a value, treat 15 as our b value. Enter in our calculator again. Oops, sorry, this should be just 15 minus 10, so this should just be 5 here. My traffic flow function is located under y1, so vars, y vars. Okay, so average value, we're going to keep the units of f of t. So we're going to be able to maintain it as 81.899 cars per minute. Average traffic flow. All right, part D. What is the average rate of change of the traffic flow? So now it's not this different, right? Average rate of change is different from average value of the traffic flow. So average rate of change is just asking for slope. What is the slope of the traffic flow between 10 and 15? So we want to find the change in traffic flow divided by the change in time. So f of 15 minus f of 10 divided by 15 minus 10. So I have y1 holding my traffic flow expression. So f of 15 minus f of 10 gives me 7.587. Divided by 5, 1.517. So we have something that is in terms of starting off in terms of cars per minute, but then we're doing cars per minute. So we're doing the rate of change of traffic flow. So we're going to have to dip down one. We have to include another rate of change there. So it's going to be cars per minute squared. Okay, any questions there? All right, I'm going to skip to number 5. Let's see. All right, so it says, number 5 says, the amount of water in a storage tank is modeled by a continuous function between 0 and 7 hours. In this model, rates are given as follows. The rate at which water enters in the tank is given by f of t. So this 100 t squared sine root t is this curve that you see here. So we can tell that more and more water is entering into the tank. So basically, it's like a faucet where they just keep increasing the amount. So we see gallons per hour will keep rising over the course of this 7-hour period. Okay, so more and more water, the rate at which water is being added, we can see it increasing. The rate at which water leaves the tank is 250 gallons per hour between 0 and 3 hours. So water is leaving the tank at this rate of 250 gallons per hour. But then after 3 hours, they're going to switch it to be a lot more. So all of a sudden, it's going to jump directly from 250 to 2,000 gallons per hour. Okay. The graph of F and G intersect at t equals 1.617 and t equals 5.076. I'm going to identify those t values there. And then at t equals 0, the amount of water in the tank is 5,000 gallons. So there's water in the tank to begin with, but you can imagine because of these rates, the amount of water in that tank is going to rise and fall depending on what's happening at that moment in time. Okay, part A says how many gallons of water enter the tank during the time interval. So we just want to know how much water has been added. And we know that it's just purely based off of this formula, right? This is the only formula that is providing information about how much water is being entered in, right? The rest of the information is either what's already inside the tank to begin with, or what's leaving the tank. The only thing giving us anything about water entering the tank is this f of t. So if I want to get from this gallons per hour to be total gallons, I'm going to have to accumulate this rate over this period of time. All right, basically, I'm finding the area under this curve. So I'm going to have to find the integral of f of t over the 7-hour period, and that's going to tell me how much water has entered in the tank in that time period. So I want to convert from gallons per hour to gallons, take the integral. All right, you can enter all this into your main screen. I'm going to put it under Y1. Again, make sure you're in radian mode. Main screen here, Math 9 from 0 to 7. Bars, Y bars, function. So over the 7-hour period, there's going to be more than 8,000 gallons entering into the tank. Round to the nearest whole number here. Okay. Now that doesn't mean that there's going to be this much water in the tank, because we have water that's being let out of the tank because of these rates here. Okay, but this is part A. It's just asking how much water enters in the tank, and that's what we have. Okay, part B, find the time interval when the water in the tank is decreasing. Okay, let's talk about what this diagram is showing us. So we know that there's water in the tank to begin with. Water is going to be entering the tank, but then water is also leaving. So basically, whenever whichever has a higher value is going to dictate whether the water level is rising or falling. So here, I want you to observe what's happening here between 0 and 1.167. Notice how my horizontal line is above the curve. So what that means is that the rate at which water is leaving is more than the rate at which water is entering into the tank. So if I'm letting out more water than I'm bringing in, what's happening is that the water level is going to be dropping. So I'm going to indicate, I'm going to highlight with red to indicate that my water level is dropping in this time interval because the rate that the water is leaving is greater than the rate at which water is coming in. Okay. Now, after it hits this point, then what's going to happen is this faucet that's being turned on is all of a sudden you're going to get to the point where it's going to be above this rate at which water. So water is still being let out, but the rate at which water is coming in is now greater. So now the curve is more. I mean, the amount of water coming in is more than the amount of water being let out. So in this next time interval, we're going to expect our water level to rise. So it's going to be rising. So I'm going to use the yellow to indicate rising here. It's going to be rising in this time interval. But then, even though the water is being let out, it's going to keep rising. All of a sudden, the rate at which water is leaving is going to be switched up all the way to 2,000 gallons per hour. So then this next time interval, water level is going to start dropping again because now we're letting water out faster than the rate at which water is coming in. Okay. So again, I'm going to indicate with red here that the water level is dropping here. But then eventually, after 5.076 hours, the water that's being let in keeps rising and rising, and the rate that the faucet or that the rate at which water is coming in keeps growing to the point that it's going to rise above 2,000 gallons per hour. And so this final stretch, even though there's a ton of water being let out per hour, there's going to be even more water being let in, more than 2,000 gallons per hour. So I'm going to indicate that with yellow again. So we can basically, looking at this diagram, we can conclude that water level is dropping, but it's going to rise from 1.617 to 3. It's going to fall again, and then it's going to rise from 5.076 until 7. Okay. So using that visual diagram, I think we should be able to answer part B. Part B says, find the time interval in which the amount of water in the tank is decreasing. Okay, so we know the tank is decreasing in the red that I identified. Okay, so we can say the amount of water is decreasing. On the time interval from 0 to 1.617. And then also on the interval from 3 to 5.076. And the reasoning is simply because our G of t is greater than F of t, right? The amount of water leaving is more than the amount of water being let in per hour. So part C, For time between 0 and 7, at what time is the amount of water in the tank the greatest? So here we see we're trying to find the absolute max. So anytime we're looking for absolute max, we have to involve EVT. Excuse me. So to do EVT, or to apply EVT, we have to identify our endpoints and then critical points. But in this case, we only care about relative max. There's no need to test relative min because we know that relative mins have no chance of being an absolute maximum. So we only care about the max, so we only need to test endpoints and relative max. All right, so we know we have to test t equals 0. We have to test t equals 7. But let's see where the relative max is. So here, all right, we see the water levels dropping, and then all of a sudden it's going to start to rise again. Well, we call this a relative minimum, right? Because water level is going to drop, but then it's going to start rising because of the yellow here. So we don't care about relative minimum, right? There's no way this can be the absolute max inside the tank. All right, but the water level is going to rise. It's going to rise, but then at this point, it's going to start dropping again. So it's going to rise followed by dropping, and so we can say that yes, there's a relative max at 3 because that water level is going to hit some relative max, and then it's going to start to drop after that. So we have to test t equals 3. Then it's going to start dropping. So it's going to drop until it rises again at 5.076. So this is another relative minimum. And so there's no need to test relative minimums. So it's going to fall, then it's going to rise again, and there's our endpoint. So we only need to test 3 points. We only need to know how much water there is at 0, at 3, and then at 7 hours. So let's find the amount. I'll call it A of t. Okay. So A of 0, right? I think they gave that information to us. They said that at 0 is 5,000 gallons. All right, we need to figure out how much water there is in the tank at 3 hours. Remember how for number 3 from when we did number 3 with the amount of sand on the beach. Anytime we're talking about amount, there's 3 things we got to consider. We have to consider the initial amount plus the amount added minus the amount removed. So it's the same idea here. We have to take all 3 things into account to figure out how much water there is in the tank. So we know that there's 5,000 to begin with. We know between 0 and 3 hours, we can accumulate how much water has been added in that time period from 0 to 3. So I think I made a mistake on the key here. I think I wrote 0 to 7, but it should be 0 to 3. So this is how much water is accumulated based off of how much has entered into the tank. But then we also are removing a certain amount. We're removing 250 gallons per hour in that 3-hour period. So we need to include that as well. So we can either think of it as the integral from 0 to 3 of 250. But it's a constant rate, and you can just do this in your head as well. You can just say 250 times 3 is just 750. So either way, it's the same answer. You can plug this in the calculator as well. So 5,000 plus the amount accumulated in that 3-hour period added to the tank minus the amount subtracted from the tank. So I already have Y1 holding my the amount of water in the tank, or the rate at which water is coming in. So I'm going to go from 0 to 3. But I'm going to subtract out the amount of water that's been removed. So from 0 to 3, 250 is the rate, dt. So we know that at 3 hours, there's going to be 5,126 gallons of water. And then finally, our last candidate is the other endpoint, A of 7. Okay, so we start off with 5,000. We want to do the full accumulation. Oh, you know what? Let's do this. Because the rate is different, let's pick up where we left off and say that, okay, from after 3 hours, at the 3 hour point, we have 5,126 gallons. So we're just going to pick up where we left off from there. I think that's going to be a little cleaner, especially with the rate being different here. So let's say that we're going to start off at the result, or the amount of water in the tank at 3 gallons. Sorry, at 3 hours. And then we're going to find the accumulation of water between the 3rd and 7th hour. That's the integral of f of t from 3 to 7. And then we're going to subtract out however much water has been removed in that 4 hour period. And that's a different rate, right? Because all of a sudden we have more water leaving the tank, 2,000 gallons per hour. Okay, so that's a little bit cleaner here. Okay, so this is how much water there is in the tank at 3 hours, how much water has been added to the tank between the 3rd and 7th hour, and then how much water has been removed from the tank between the 3rd and 7th hour. If we total those together, we're going to know how much water there is in the tank at the 7th hour. Okay, I'm just going to update my entry from the previous time. I want to go from 3 to 7, and then from 3 to 7, but I have a new rate, so my rate is now 2,000. So looking at my candidates here, I have 5,000 gallons versus 5126 versus 4513. So my absolute max must be at 3 hours. It says justify, but if you just show your work for extreme value theorem, that's justification for your work. All right, I want to go to the other worksheet. I think 6 is good, but I have a video for number 6, so if you have questions about that, you can ask me later, or you can look at the video that I included under number 6, or under this day's date. All right, so this is homework 5B. All right, it says we have the graph of f consisting of 4 line segments, so 1, 2, 3, 4. let G be the function given by G of X. Part A says find G prime of 1. All right. Whenever you see this notation, that's indicating to us that there's a special relationship between G and F. And that relationship is the fact that this F is sitting basically at the derivative level of G. Okay? Because in order for these two to be the same, I got to take the antiderivative of F to bring it up to the same level as G. That means F is sitting at a level below G. Okay, so because of that, we can really think of this F as a G prime. Okay, but I want to show that really we're just applying second theorem. So let me put this over here. If I want to show that G prime is basically F, because if I do want to find G prime, and if I put a derivative notation in front of integral to indicate that I'm trying to establish that derivative, then this is really applying second theorem. Second theorem says derivative and integrals will just cancel each other out. The upper bound is going to get entered into the function, and then we're going to multiply by the upper bound's derivative. So just as a reminder here, second theorem looks like this. Right. We put the upper bound into the variable of our function, and then we multiply by the upper bound's derivative. So if I did that, the x gets inserted into the t, so all of a sudden it becomes f of x times the upper bound's derivative, so no impact, times 1. So basically I can say g prime is equal to f of x. So that tells us that they tell us this is the graph of g, but we can also give it another name. We can say that this is g prime. All right, so we're really just looking at a G prime graph. This is the G prime graph. All right, so that's what they're trying to establish with this information here. Part A says find G prime of 1. Well, if this is the G prime graph, then I can find G prime of 1 just by entering 1 into my order pair, right? If this is my G prime, then I just need to find the order pair where this is. So G prime of 1. We see that the y value on this G prime graph is at 0. So f prime of 1 is the same thing as f of 1, which is 0. Part B, find the x coordinate of each point of inflection. Well, of G, so if this is G prime, then we can pick off point of inflection by, if you remember, anytime we're looking at the first derivative graph, point of inflection is located peaks and valleys of our G prime graph. So for B, I'll create a second derivative sign line. I'll place my critical points there, 2 and 6. This is a negative slope, which is going to correspond with concave down. Positive slope is going to correspond with concave up. Negative slope corresponds with concave down. So we can say that because there's a change in sign at these critical points, that we have point of inflection at 2 and at 6, because G prime changes from decrease to increase or from increase to decrease. All right, part C. Find the average rate of change of G. So whenever we see the word average rate of change, we think in terms of find the slope. So part C, average rate of change. G of 8 minus G of 2 over 8 minus 2. Now, how do we find G of 8, G of 2? We have a formula for G of X, and this is our formula. -2 to the X value. So basically, we need to accumulate area in order to we need to accumulate area in order to find the depth integral. So let's gather that information. Let's find G of 2 first. So if I want to find G of 2, the formula says integral from -2 to X. My X value is 2. So I need to accumulate the area from -2 to 2 under my f of t graph. So from -2 to 2, I'm looking at the area of this region here. I have a triangle, 1/2 base times height. I have another triangle here, 1/2 base times height. This is above, that's below. I need to keep track of positive and negative. So 1/2 4 times 2, or 3 times 2 rather, 1, 2, 3. And then here, this is below the x-axis, so this, I gotta make sure that's a negative region here. So 1/2, 1 times 3. So I get 6 over 2 minus 3 over 2, which is 3 over 2, which is 1.5. Next up, I need to find G of 8. So G of 8, depth integral from -2 to 8 of f of t. So now I need to accumulate this entire region here. So I need to total up all these triangles. Okay, so first triangle, 1/2 base times height. Second triangle, I'm going to find this entire triangle now. So that's 3 times 3, but it's subtraction because it's below the x-axis. Back to above the x-axis, so base of 4, height of 3. So I have 6 over 2 minus 9 over 2 plus 12 over 2. That reduces to be 9 over 2, which is 4.5. So now we have enough information to find the average rate of change. So we say 4.5, that's G of 8, minus 1.5, that's G of 2, over 8 minus 2. So 4.5 minus 1.5, that's just going to be 3. 3 over 6 is 1/2. 1/2 is the average rate of change. Part D says, for how many values of C is G prime equal to the average rate of change found in part C, which is 1/2. So G prime is, this is my G prime graph. So basically just saying, how many times is G prime going to hit 1/2? Well, I'm just going to draw a line where I think 1/2 is. I think it's going to touch it. Oh, it says for how many values? Between 2 and 8. Okay, so between 2 and 8, we see there's a value here, but that's not part of our interval, right? Interval is going to be between 2 and 8. So we see once here and once here, so that's going to be twice. Okay. All right, any questions there?
That last section, D, was that just like a visual?
It really is. Yep, it's a visual. It's just wanting us to be able to see basically intermediate value theorem, but it's really just, yeah, looking at it, looking at the graph and understanding that we do need information from part C in order to answer part D appropriately. Yeah, and also students have to understand that G prime, that this is G prime, right? This is the G prime graph. Okay, I think 2 is pretty easy, just approximation using trapezoids. D is just applying second theorem. I just want to run through 4 through 6, and then I want to do number 7. Okay, so I just want to run through 4 through 6 through the key, just see if you guys have any questions here. It says find f double prime at 1, which means we got to go through the derivative twice, right? So to get f prime, notice that this is set up as a definite integral. So to get f prime, we only need to apply second theorem. So second theorem just says insert the x squared into the variable, and then multiply by the exponents by the upper bound's derivative. So really, we're just applying second theorem to get to f prime. Right. So my function is defined with the integral in front. So if I want to find the derivative, I'm just going to have just follow the rule here. Insert the variable into t, and then multiply by x squared's derivative. So that's what I did here. Inserted the x squared in for the t in the numerator and denominator. I get x to the 4th plus 3 with the square root all over 2x squared times 2x, because 2x is the derivative of the upper bound. I reduce that, and I get it down to square root of x to the 4th plus 3 over x. So that only gets us to f prime. If I want to find f double prime, I have to find the derivative of this expression again. And this kind of goes back to first semester. First semester says if I have 2 expressions divided by one another, and if I want to find the derivative, I got to go through quotient rule. So my entire numerator is my f, my denominator is my g. So this whole portion is my f prime, because I have to go through chain rule, because I need to find the derivative of x to the 4th plus 3 to the 1/2. So I need to take the outside function's derivative, which becomes 1/2, x to the 4th plus 3 to the negative 1/2. That's the outside portion's derivative. Multiplied by the inside portion's derivative, x to the 4th becomes 4x cubed, and that will complete my f prime. And then g minus f g prime, all over g squared. Now that I have my derivative, my second derivative, I can enter 1 in for all the x's, and then just a matter of trying to cleaning all this up. So 1 plus 3 is 4. 4 to the negative 1/2 is really just 1/2. And so that's going to just clean up to be just 4. Wait, let's see. So 4. Is that right? Let's see. Yeah, so this is 4 to negative 1/2, which is 1/2. So 1/2 times 1/2 is 1/4. 1/4 times 4 is just 1. Yeah, so this whole thing is just 1. 1 minus 4 is 2. 1 minus 2 is negative 1. All over 1. So my result is just negative 1. Number 5 is, we did this in class, similar to this, where we understand if we're dealing with an absolute value function, let's draw the graph. We know our vertex is at -1, whatever makes the inside portion equal to 0. And then we extend the graph on both sides, and then we're just totaling up the areas of these two triangles. So 1/2 base times height, 1/2 base times height, we're left with 41. Number 8, I want us to be able to see that this is really just kind of a particle motion problem involving finding kind of a first theorem variation here, where I can think of it as final position equals initial or starting position plus displacement. So if I want to find f of 5, I can basically start at -1, and then I can accumulate my progress from -1 to 5 under my f prime graph. So this is my starting point. This is how much progress I made, and then this is where I end up. So 1.5 is f of -1. Enter this in the calculator. That will tell me the progress I made, 1.524. I start here. I made this much progress. I end up at 3.024. All right, let me go over number 7. 7, they're telling us to go through use substitutions. So we're going to go through use substitution, convert the bounds, and see which what our result is going to look like based on the answer choices. So I'm going to go ahead and replace the 2 minus x with u. So once I do that, I also need to start to get my x's, get these portions in terms of u. Maybe I'll just work this out from scratch here. So number 7. If I rewrite this as x, 2 minus x to the 1/2 dx. Okay, so they're telling us our u value is 2 minus x. Yeah, so this is kind of a straightforward problem, but we have to leave everything in terms of u here. So our u value is 2 minus x. Our derivative, du dx, is just -1. We solve for dx. dx equals negative du. We make our substitution. But the x's do not go away. Nothing cancels out. So this is a change of variable. Where we have to find a way to get that x to be resolved. So we look at our assignment between u and x, and if I can rearrange this, I can get that x to disappear. So I'm going to solve for x. X is equal to 2 minus u, and I'm going to take that and reinsert it into my expression. I'll push the negative outside in front here, but I replace the x with in terms of u. All right, we're getting a little closer to our answer choices, but we have to adjust our bounds because right now our bounds is in terms of x, and if you notice here, there's bounds involved, but all these have to be in terms of u because our integrand is in terms of u. So we're going to push these bounds to be in terms of u from x. We're going to convert the bounds. So our old lower bound is x is 1. So if I push that through my conversion, if I replace 1 in for x, 2 minus 1 is just 1. So looks like my old and upper bound did not change, but we still have to push it through that conversion rate. My old upper bound was 3. So u equals 2 minus 3, which is -1. So if I rewrite this, I have negative integral from my lower bound was 1 and my upper bound is -1. Now notice that my upper bound is 3, but it ended up being lower than my lower bound, but it's okay. Wherever you start it is where you end up. So even if they end up not being out of place. Oh, let's see, made a mistake here. Yeah, that's right. Okay. Okay, so that -1 is going to stay up there for now. And then we have 2 minus u. Wait, let's see. X is equal to 1. 2 minus 1 is 1. -1, okay. Okay, so from 1 to -1, if I plug 3 in for x, u equals 2 minus x, right? Yeah, u is 2 minus x. Okay, my upper bound is -1, my lower bound is 1. There's still that negative that's sitting out in front here. So it looks like the answer choice is flipping the bounds. And when it flipped the bounds, it's going to push that negative away. So if we do that, we get from -1 to 1 of 2 minus u times u to the 1/2 du. But looks like the answer choices looks like it's not quite matching up the way that I thought it would. Okay, so let me look a little further into this. I don't know if I made a mistake somewhere in between here, but I had to hold on to that negative exponent. Okay, so answer choice was supposed to be D, but I'm getting something that's a little bit different with that u minus 2 versus 2 minus u. Okay. I don't know if you guys see anything different from what I'm seeing with number 7. Upper bound, -1. Okay, let me look at this a little further. It should be D. It's pretty close to D, but for some reason, I'm not quite getting that result. So I may be missing something. Okay, I'm going to stop this session, and I'll open up the next one for the FRQ homework. So, all right, if you guys want to join, great. But I'll see you guys in a little bit.